Okay, so let's take a look now at some of the very simple devices that we can use to perform reactions or to carry out procedures that will allow us to determine and calculate enthalpy changes, heat changes for chemical reactions. So the first one is constant pressure calorimetry. And again, constant pressure is typically what we would see in the laboratory when the pressure doesn't change if at all. And we're assuming again in normal conditions that pressure isn't going to change. A very simple calorimeter is called a coffee cup calorimeter, and all this involves is just two styrofoam cups that are nested. The two nested styrofoam cups, coffee cups in other words. And again, these are needed because these are very good insulators. They won't lose heat to the surroundings. They won't absorb heat, for instance. So they're really good at keeping a hold of what's going on inside. So these can be used to measure heat changes or heat exchanges for a variety of reactions, again, at constant pressure. And several of these you would have either done already or you will be doing in the laboratory. You'll be making some very simple measurements to determine these. So the idea behind this is very simple. We have here two nested styrofoam cups. There's one on the outside, there's one on the inside. And then we're going to provide a lid to it, again, to make sure that we don't lose any heat to the environment or absorb any heat from the environment. We have our reaction mixture that is in the inside, and we have a thermometer, obviously, that is then going to measure temperature changes. That will give us our delta T, or thermometer. We can measure the mass of everything inside by just taking a difference, measure the mass of the coffee cup empty, put our stuff inside, then we measure the mass of it again. So we can get our masses that way. We get our delta T's, and then we can look up the specific heat of the stuff that's inside, and we can use our Q equals MC delta T in order to calculate our heat changes. So a couple of things to consider when we do use the coffee cup calorimeter. The system is going to be the reactants and products, which is going to be happening in the reaction inside here. And then the surroundings will actually be the water in the calorimeter. That will either absorb the heat or provide heat to the system. So for exothermic reaction, again, the system is going to lose heat to the surroundings. The surroundings then will gain or absorb that heat. And again, there is no overall change in heat energy for the system plus the surroundings. So that then is going to be the change in heat energy for the universe is zero. We can make the equality such that Q, the heat for the system. And again, remember, the heat on the constant pressure is the same as enthalpy. Okay, so QT there, this is heat on the constant pressure. That is the same as the change in enthalpy. Okay. So Q of the system would be equal to the negative value of Q of the surroundings. Okay, or we can say negative Q of the system to be equal to positive Q of the surroundings. Okay, so if we can measure the surroundings, so the M, the C, the delta T for the surroundings, we plug that into our equation. That's equal to the negative, the opposite sign of the Q of the system. So it's a very, very simple process that can be used. However, you want to keep track of the sign so that we don't make that mistake when we do our calculations. All right, let's take a look at an example. So it says a metal pellet with a mass of 100 grams, originally at 88.4 degrees Celsius, is dropped into 125 grams of water at 25.1. The final temperature of both pellets and water is 31.3. Calculate the heat capacity in joules Celsius of the pellet. All right, so the system here is the pellet. the surroundings is going to be the water in the styrofoam cup. And for the pellet, we have the mass that is 100.0 grams. For the water, the mass of the water is 125 grams. And we're given we're given temperature. So the initial temperature here for the pellet, TI is 88.4. We see the final temperature of the pellet. This is the same. The final temperature of the water is 31.3 degrees Celsius. For the water, the initial temperature of the water is 25.1 degrees C. The final temperature of the water is 31.3. It's the same as the pellet. And that's all the information that we're given. All right, so what we can use then is our equation, because we're asked to find the heat capacity, C. So we're going to use Q equals C delta T. So this now is the heat capacity, not the specific heat capacity, but the heat capacity of the actual thing, as opposed to kilogram. And what we're given, what we need to find is heat capacity of the. Okay, so we have more information about the water, so we can start with this. So we can calculate Q of the surroundings. That is equal to the heat capacity of the water times delta T of the water. All right, so we have, let's see here, we have our heat capacity. In order to do that, we need to use a specific heat, which is the 4.184 joules per gram degree Celsius. We have to times that by the mass of water that we have, which is 125 grams. That goes away. Oops, leave it here. So we have a heat capacity then in joules per Celsius. And then we need our delta T. Okay, so the delta T there would be final minus initial. So delta T for this would be 31.3 minus 25.1. That would give 6.2 degrees Celsius. That's our delta T for here. 6.2 degrees C. Degrees Celsius go away. So we end up then with Q of the water, which is the surroundings, is equal to 42.6 joules. Now, the temperature of the surroundings increase, right? So that means it absorbs heat. So this is going to be a positive value, which means the Q of the system then, it's what? Has to be the same value, 42.6 joules, but it has to be negative, right? So again, Q of the system being equal to the negative value of Q of the surroundings, or negative Q of the system equal to the positive value of Q of the surroundings. So we're making that equality because we know the amount of heat lost by the pellet would be equal to the amount of heat gained by the water. All right, so now we can take this, plug it into our heat capacity equation for the pellet. So we can say Q of the system is equal to negative 3242.6 joules. And that is equal to the heat capacity of the pellet times delta T. Okay, and delta T for the pellet now. So the final minus the initial here, so delta T is 31.3 minus 88.4. So that's going to give you a negative value because the temperature went down. So that's negative 57.1 C. So what do we have? We have negative 324.2.6 joules equal to C the pellet times what was that? Negative 57.1 degrees C. So then the C of the pellet, heat capacity of the pellet is simply negative 3242.6 joules divided by negative 57.1 C, and then we'll end up with 57 joules per degree Celsius of that amount of the pellet that we have. So that's using the constant pressure calorimetry, and again, making these equalities here. The heat of the system is equal to the negative value of the heat of the surroundings will allow us to solve that. Constant volume calorimetry is slightly different. Here we use a device that's a little bit more sophisticated. It's called a constant volume bomb calorimeter. And this is an isolated system, right? As opposed to the constant pressure one, which is not. So here, we use the bomb calorimeters to determine usually the heats of combustion of reactions. And here we actually can use the equation, the heat of the calorimeter equals the negative value of the Q of the reaction that we're studying. This is often used, this technique is used for determining energy content of foods, right? Or consumable items. If you ever look on the nutrition label on anything that you eat or drink, there's usually a label that tells you what the energy content is in calories. How do they actually determine that? Well, they use a constant volume bomb calorimeter. So this is it's an isolated system. It's insulated very well. At the center of it, we still have something similar that looks, like the calorimeter before. We have the bomb itself, which is sort of the inside of this. We have our sample that contains the whatever sample is that we're trying to combust or burn. We have an ignition wire that leads to the outside, and our samples in here. So what happens is as we burn the sample, heat is produced, and the heat then warms up the water that surrounds the sample cup or the bomb itself, and we can measure the temperature change of the water, and then using that in conjunction with the heat calorimeter or the capacity of the calorimeter, we can determine what the energy content of the sample is. So the idea behind it, again, is very, very similar to the one that we looked at previously. So here we have an example. We have a bite-sized cookie, chocolate chip cookie weighing, what is it? Famous. It weighs 7.25 grams, and it's burned in a bomb calorimeter. So what they do is they take that cookie and they put it here. That's where the cookie is. They light it on fire. They burn it in the bomb, and that causes the temperature of the water on the outside to increase. And they can measure the temperature in a thermometer, and they measure that temperature change to be, it went up by 3.9 degrees Celsius. They know they've calculated previously the heat capacity of the calorimeter itself. The device itself is 39.17 kilojoules per degree Celsius. What is the energy content in kilojoules per gram of the cookie? So we're using the same idea that we looked at before. Actually, the Q of the reaction would be equal to the negative value of the Q of the calorimeter. So in other words, the energy that is either absorbed by the reaction or that is absorbed by the reaction is the energy that's released by the calorimeter, or we can do the opposite as well. The energy that is released by the reaction is the energy absorbed by the calorimeter. So the Q of the calorimeter, again, cal here is the calorimeter, is the specific heat of the calorimeter, which is 39.97 kilojoules per degree Celsius times delta T, and it gives it the delta T is 3.90 degrees Celsius. So that goes away. Okay, so that's going to give us whatever that is. What is that? 1.559, so about 156 kilojoules. Okay, and that's equal to the negative value of the reaction. Okay, so that tells us that that's the amount of energy then absorbed by the calorimeter. That's the amount of energy released by that reaction. And that is the energy in for that sample, and that sample is 7.25 grams. in order to get the energy content in kilojoules per gram, we need to divide this by the mass in grams, and that was given us 7.25. Okay, so we take that 1.559 times 10 to the 2 kilojoules, we divide by the 7.25 grams, and we end up with 21.5 kilojoules per gram for that particular chocolate chip cookie.